Good evening, welcome to Lecture 9, Energy and Work. Here are your learning intentions and success criteria. Please complete the KS table. Pause the video while you complete this. Okay, so having a look through here, we're looking about understanding energy and work, and what we're trying to be able to do is interpret force displacement graphs. Through success criteria, we've got this define. We've got a few things we need to define today. We need to be able to calculate work done by a force, so there's an equation that's going to have to come into that, and we need to be able to interpret a force displacement graph. So some of the things, well, we should know what is work, we should know what is energy, and finally, what is a force displacement graph? These other things, kinetic energy and gravitational energy, we did cover that in grade 8, so hopefully you can remember some of those things. Skills, can you calculate work? And finally, can you determine the area under the curve for a force displacement graph? So, in grade 8, when we first talk about energy, we're told about several different types, and a couple of these we'll keep using through the whole course, and a few we're going to just discard because they're not really that useful anymore. And the good news is the first couple we're going to look at are the easy ones. So we're going to look at kinetic energy, and we're going to look at gravitational potential energy. And here are the symbols that we give them. Notice the capital E in this case stands for energy, and we're just going to use a small subscript to say EK for kinetic and EP for gravitational or gravitational potential. Some texts like to write EGPE. Some texts will just call that whole thing potential. So just be careful about that. Now, collectively, these two are going to be called mechanical energy because they both deal with motion and position of an object. Now, the total mechanical energy something has is just the sum of these two things. Kinetic energy plus potential energy equals mechanical energy. Now, this EM doesn't appear in the syllabus or in the textbook. Some will call this the internal energy of a system. In our syllabus, we're calling the internal energy something else that we'll deal with later. So just be aware of that when looking around different resources. This formula also does not appear in the textbook at all, or in the equation booklet at all. So just be careful of that. If you might need to remember that. So this is going to be the symbol I'm going to use as reference. It's not the strict definition, but it's one that will be useful for us. The other types of energy that we've learned about in the previous, things like chemical energy, thermal energy, nuclear, electromagnetic, these things that an object might have, they're called internal energy, and I'd recommend really reading the text about that. And we'll look at them later on. If you're doing chemistry, you'll look at some of them in chemistry, and the symbol that they give at the moment is the letter U. I know the letter U does not appear anywhere in the word internal energy. Why not E subscript I? Just the way that it is, unfortunately. As a recollection though, energy has the unit of joules. We give it the symbol capital J. It is named after a person, so capital letter. So, work. What is work? The definition for work in the syllabus and in the textbook just gives us a formula, so we need to come up with something that's a little bit better. I would consider it work is the movement of energy, measured in joules. Okay, because it's just moving energy, it's still energy, so it's in joules. And so this gives us a really simple equation that pops up in the text. Work equals delta E. Work is the change in energy. Now, energy is always positive. With these previous formulas, the energy will always be positive. However, sometimes the work being done will be negative if a system loses energy. We'll look at gravitational energy in a little bit more detail in video 110, but as we raise objects, we can say that it is gaining energy, but if it's dropping, it would be losing gravitational energy because it's changing out of the system. So, normally though, this work means that something useful is happening. Work might be done by the electrical circuits in this tablet to turn electricity into light. Okay. One common bit of language that pops up though, in the text especially, is work being done by something, or work being done to, or sometimes on something. And the text doesn't really describe it well, so I'm going to give you a little bit more information, but the good news is that this language doesn't appear much in the syllabus at all, so it's not super critical for you to really get the nuance of it. If you want to do further studies in physics at university, then you really want to knuckle down on a little bit, and there's some good descriptions out there. So if work is done by gravity, then work is being done to an object, and it always comes in pairs, like we learnt with force pairs, and there's a reason for that. So the examples that the texts give are about a roller coaster. The roller coaster going down, the work is being done by gravity and to the roller coaster. If the roller coaster is going up, then the work is being done by the roller coaster to gravity. And I don't think the textbook really describes it very well. In fact, I think it flat out gets it wrong. But it won't matter for the content level that we're dealing with. You're not going to have to be careful about, oh, is this a by or is this a to, and worrying about, signs. If that does appear later on in future versions of the syllabus, then we'll clarify that a little bit more. Okay, so this is some of the important part about work. So let's get into the actual math side of it. In physics, we define work when a force has occurred over a displacement. So that has to be movement. If I make you hold your arm out and put a book on top of it, if you don't move the book, you're not doing any work against the book. You might get tired, but you're not doing work to the book, because the book is not moving. This is also the textbook definition. Now, sometimes in the syllabus this is called mechanical work, rather than just work in itself, because it's about mechanical energy and movement. And so this gives us the formula for work. Work equals force multiplied by displacement. If I apply some force for a displacement, then we end up with some work being done. There's a great video by Acapella Science that uses some trashy pop song where they sing about doing work to sing about work using this equation. Worthwhile having a watch. The force and displacement must always be parallel. Okay, so let me show what I mean by this. I have a box and I am pushing it this way. This is my force, and the displacement will be here. The force and the direction of motion, being that way, is parallel. They're in the same direction. If I had a moving object, and so it had a velocity of this way, and I put a force on it this way, and so it had a displacement this way, force and displacement are still parallel, opposite directions. That's okay. Okay, that's okay, but they are still parallel, and so we can just multiply them together. Okay. If I have something like draw it up here, and then I have this object, say I'm forcing it down this way, I'm pushing down on the object, but it moves this way. Well, now the two aren't parallel to each other, so we can't multiply them together. We need to consider how much is acting in a certain direction. If work is at an angle like this, let's say that is angle theta, okay, then we have a different formula for it. And sometimes you'll see an equation for it. Sorry, mechanical work is always about movement related. I just wanted to double down on that. Work equals force times displacement times the cosine of the angle between it. So here, the angle between these is equal to 0, and cosine of 0 is equal to 1. Here, the angle between force and displacement is 180, and the cosine is equal to -1. So this means that we're taking energy out of the system because we're doing negative work. Here, though, the angle is something. And so not all this force is going to go into pushing it across the ground. Some of it's just going to go to pushing down. It's going to be wasted. We will deal with this a lot more in our next topic when we start looking at 2D motion. However, I wanted to clarify that you have to be very careful. Now, this cos theta, the y of it, we'll get into that in a later unit. But and it's not an equation that appears in your texts. So when we get back to 2D energy, or in the opportunities of 2D energy, I'll really remind you about this. That's everything I wanted to cover about force. So, force displacement graphs is our interpretation. So if we look at that equation for work equals force times displacement, we can see that we it can lend itself to being graphed. Force is something pretty easy to measure, displacement is very easy to measure, and so then based on what we've seen with our velocity time graphs and our force time graphs, being as we're just multiplying these two together, then on a force displacement graph, the area must equal the work being done. Now here are some examples from the text. So here's our first one. We can see here our force is a constant 150 newtons, and it goes for a displacement of 100 meters. So for this one, our work would equal Fs equals, well, force is 150 for the whole time, times 100. So we would just be 1500 joules. Okay, nice and straightforward, just need to the area. The second one here, a little bit trickier, because not only do we have this box first, but we've also got this triangle on top. Same thing, we just need the area. So we're going to need the first bit. I'm going to say work total equals the work of A plus the work of B. We'll use these separations. So that's going to equal force times displacement of A plus force times displacement of B. For A, we have 100 times 100 plus B, well, we have a height of 100 to 200 is only 100. Now, I couldn't have said 200, because if I said 200, I'm working at the area of the whole thing underneath it, and I'm not trying to do that. I just need this bit on top. So you be careful with composite shapes like this. You're just working out this extra bit. So our force was 100. 200 take away 100 is 100. Our displacement is from 40 to 100 is 60. And it's a triangle, so we have to divide it by 2. Don't forget that bit. And all up, well, 100 times 100 is 10,000. 100 times 60 would be 6,000. Divided by 2 is 3,000. So that equals 1,300 joules. Okay. And note, this shape here looks a little bit bigger than that previous one, but that's just a trick of scale, so don't be fooled by that. Finally, well, what do you do if it's not uniform, like with a spring here? Springs don't have uniform force. The more you squish it, the more you displace it, the greater the force gets. The more you stretch it, the greater the force gets. We would do the same thing, like I did over here, actually, so I've already shown you how to do this. We would just work out the area, but we would consider the fact that, yeah, this is a triangle. Base, note, that's in millimeters. You'd have to convert that to meters, and that's in newtons. Always be careful, look at the units. In fact, I should go back and double check those units because I didn't check on that first one. Newtons, meters. Newtons, meters. Notice here that the force applied east and displacement east, they are the same direction, and so it's a positive value. If this had been force applied west and displacement east, we would end up with a negative number because those would be in different directions to each other. Same thing with the next one, that was east and east. Okay, so in this video we've learnt the following. We have defined work, kinetic energy and gravitational energy. We've learnt basic calculations involving work from a force, and finally we've interpreted the area of a force displacement graph, and so hopefully you should be able to do those 3 criteria there. For your entrance to class, please check your learning question, chapter 13.1, questions 1 to 2, and 13.2, questions 1 to 6. Submit them on the 1.9 space on eLearn. Thanks very much. Catch you next video, guys.